Okay, everyone, welcome back. Hope you all had a good afternoon tea. Next up, we have a talk titled Learn Complex Skills from Anywhere, combining Django, Ansible, and OpenStack to teach any tech skill. Our speaker today is Florian Haas. Please, can you all give a warm welcome to Florian Haas.
Okay, last chance to snap the QR code if you want to follow along. Going once, going twice, sold. All right, hello, good afternoon. My name is Florian. I'm here to tell you about a set of tools that enables people to learn complex and sophisticated software technology, and in principle, any such technology, with minimal investment in infrastructure. Now, this talk is scheduled for 45 minutes. And if my rehearsal timing is any indication, then I might be filling that time slot completely, and we might not have time for questions in the end. Thus, and since the LCA crowd is normally very active on Twitter, here's what I'd like you to do. You see my Twitter handle up there on the screen. So if you have a question, please simply blurt it out on Twitter, tag my handle, and maybe add the LCA 2019 hashtag. And if you're lazy, here's a QR code that you can snap that will populate your Twitter client with exactly that. I have my Twitter notifications open here, so if there is a question that I can answer straight away, I will happily do that. And if there's any questions that I cannot get to during the talk, I'll be more than happy to respond to you afterward. And if you're coming from the future and you're watching this on YouTube, then this also gives me the option to reply to your questions later. Now, a couple more QR codes coming. Bear with me, keep the phones out. At LCA last year, in the education mini-conf, I already did a talk on a similar topic. However, at the time, I was really focusing on the educational aspects of what I'm about to talk about, whereas this time, I'm going over the technical details of such a platform. But if you do want to go back to what I covered last year, there is, of course, a video, thanks to the wonderful AV team from LCA 2018, and the YouTube link is here. And now for my last link and my last QR code, in addition, opensource.com are running an article this month on their linux.conf.au speaker series. I have an article in that series that just went up late last night, in which I explain some of the things that I'm talking about in this talk and some of the things that I talked about in last year's mini-conf talk. So that is, however, quite condensed. It's only about 1,000 words, but if you want to read up on this or want to follow this information, want to forward this information or this article to a colleague, coworker, friend, then feel free to do that. So with all of that out of the way, let's get started. I'm talking today about a sophisticated learning platform, one that is currently used by over 30 million learners worldwide, that strongly trends upward. A platform that is completely open source, and it's a platform that you can work with. That is to say, you can learn on such a platform, you can teach and create learning content on the platform, and you can run and deploy and operate it yourself, and today I'm going to show you how to do all of that. The platform I'm talking about is primarily comprised of two things, OpenEDX and OpenStack, and I'm going to start with OpenEDX. OpenEDX is a learning management platform that originally started at Harvard University and MIT. This was 2012, with subsequent collaboration from Stanford University. And that platform was originally an in-house development of these three universities, but it was then released as open source software in 2013 under the AGPL. That is the Affero GNU public license. Remember, that's the copyleft license that closes the SAS loophole. Since 2013, this platform has rapidly expanded, has been adopted by other universities, other institutions of higher learning, professional organizations, and indeed corporations. For example, Microsoft, of all places, was a then very unlikely early adopter in 2015, right? If Microsoft does anything open source today, no one bats an eye, but 4 years ago, that was still a big thing. Now, by way of clarification, I want to point out something about naming. When we talk about edX, that is edX without the open prefix, then depending on context, edX can either be edX.org, which is a learning website that serves approximately 16 million learners worldwide, with content developed in not only the three aforementioned universities where it all started, but over 60 affiliated organizations. Or edX can also refer to edX Incorporated, which is the nonprofit entity that runs edX.org, and it also drives most of the development of the platform. And that platform itself is called OpenEDX. So when we talk about OpenEDX, we refer specifically to the technology platform, and I'm going to go into that in much more detail. Now, that technology platform does run edX.org, but it also runs many, many other learning platforms that are not affiliated with edX Incorporated, the nonprofit. Anyone, including you, can deploy and run and operate an OpenEDX site as long as you comply with the terms of the AGPL, of course. And as of 2018, the estimate was that there were approximately 18 million learners on unaffiliated OpenEDX platforms on top of the 16 million learning on edX.org. It was about 2017 when they broke even, when they had just as many learners on unaffiliated OpenEDX platforms as on edX.org. And since that, the unaffiliated platforms have kind of surpassed edX.org in learner numbers. And of course, that's exactly what you want to happen in an open source project. And that gap is, of course, widening. So as I said, a little over 30 million learners worldwide. Now let's take a look at the technical components of that platform. OpenEDX, the core of the OpenEDX platform is its learning management system. Now, learning management system is a generic term, so is the initialism LMS. But in a bout of creativity, the OpenEDX developer is also called the part of the application that constitutes an LMS. And any learner and any student on an OpenEDX platform interacts with the LMS to access course content, to watch videos if the courses include them, take labs, quizzes, collaborate with co-learners, all of that. So we're going to take a quick look at what that looks like. So let's see if I get the tab switch right. There we go, right? So what you can see here is an edX course an OpenEDX course on an OpenEDX platform. This happens to be one that concerns itself with teaching the fundamentals of the Ceph distributed storage system. What you see up to here is nothing very much out of the ordinary. You get a course content overview, and then a course can have any number of sections and units, and then you basically can get started with some theoretical content that is mostly prose, and you could also include all sorts of other things like videos and what have you in there, right? So we go through here, and then what then becomes sort of a little more interesting that I'm going to get back to in a little bit is interactive lab environments. Actually, let me full screen this thing here. Go. And I'm going to cut back to my slides before I get to this. The LMS is essentially a fairly involved Django application, or rather it's a whole collection of applications, which is a theme that will be quite familiar to many Django developers. It's a relatively standard way of doing things. Also a relatively standard way of doing things is that it's not only Django, but it's Django that runs in Gunicorn, that's managed by Supervisor D, that's stuck behind Nginx. But for all practical purposes, it's just a Django application. And there are many other things about the LMS that are going to sound quite familiar to you if you've ever built a Django application. It runs in its own venv. It relies on pip packages to provide additional functionality. It puts this data into a MySQL database via the standard Django ORM layer. It makes use of the Django storage abstraction layer, and so on and so forth, right? So all of those things are very much sort of standard Django way of doing things. In case you're wondering, like, what would this thing put into a relational database? Those are things like information about users, which can be a username, but also an account profile, age, gender if you choose to give it, your name, the courses that you're enrolled in, the exercises and labs or quizzes that you took in those courses, your results on those, and also, like, if a course has something like a closing exam or certification or something like that, that would also be in the relational database. And then another important component of OpenEDX is the CMS, the course management system. Again, this thing is just called CMS as far as the Django application name is concerned, although there is a slightly snazzier alias available in that this thing is also called OpenEDX Studio. So OpenEDX Studio and OpenEDX CMS are synonymous. And the CMS is for teachers and instructors and course authors. And we can have a quick look at that as well, right? So that's a view of the OpenEDX CMS. Indeed, that is exactly the same course that you see there. You see a course outline. You can set all sorts of settings. So basically like course metadata that you can set. Like for example, when does the course start? When does it end? Does it have a number or a name or things like that? You can define whether a course is private, that is to say invitation only, or they can be public, which means they're self-enrollable courses. And then there's all sorts of other things like, you can put in a course overview and things like that, and a bunch of other settings. And you can also use this thing. If we go back to the outline here, you can also use this thing to build your course content. It basically comes with a full content editor that you can then use to build your labs and courses, etc. I said you can because you don't have to. If you are a course author who prefers to manage your course content in an external content store or in a revision control system like Git, you can totally do that, and you can then import it from there. And learners normally don't interact with the CMS at all. This is purely for course authors, instructors, and the people building content. And like the LMS, the CMS is also a Django application. Now, a brief aside here, really quickly, in that so far I've talked about an application that basically provides content to humans, so stuff that's meant to be rendered in a browser. But OpenEDX also has certain components for machine-to-machine communication. So for example, OpenEDX has an analytics framework that allows you to analyze your learners' data, like your learner's age, gender, primary language, location. Then you can correlate that with their learning success, which is super useful because that is something that you might be, you can use to detect, like, do I have hidden gender bias, for example, in my course? Do I have course content in there that makes it particularly hard for people whose first language isn't the course language, and so on and so, or age bias, or things like that. And that analytics framework also talks to OpenEDX using a REST API. And the way this is implemented is using the DRF, the Django REST framework, where you use basically the DRF to provide the REST API endpoints, and you use OAuth2 for authentication for those other systems to authenticate to the OpenEDX system. Likewise, for example, there's also a system that you can use to sell course seats. So you have like private courses that are where you sell seats for a fee, and you can also do that. That also happens via the DRF. But back to content that is actually consumable by humans. The courseware content is internally stored using a format called Open Learning XML, so OLX, that's an XML flavor, and it lives in a content store called GridFS. Now, this is admittedly a little bit quirky in that GridFS is something that more or less emulates a file system, but in MongoDB. And bluntly speaking, that's a bit of an odd way to store file-like content. It's basically a kludge, I think, for OpenEDX's use case. But this has been around for a while. Its introduction predated the ready availability of stable distributed file systems like CephFS. And apparently, NFS wasn't something that the developers were willing to consider at the time. And at this stage, it seems to be really hard to get rid of. Although, to be completely candid, it does occasionally cause headaches. And I'm talking about purely technical headaches. I'm not even talking about like licensing issues, which is a whole other issue. So with that application architecture that I just described, that leads us to a systems architecture that I've tried to put into a schema, or actually a colleague of mine, Adolfo Branches, who originally created this graphic, put into this little diagram of a systems architecture. So what we need in order to build an OpenEDX platform is we need a persistent backend that holds our MongoDB, that's the GridFS, and MySQL data. And of course, it's persistent, and we need this data all the time, so we want to build this as a high availability cluster. Right? And so for MySQL, that's typically MySQL Galera or MariaDB Galera cluster, and MongoDB, just a MongoDB cluster. That's our backend. That's shown on the left bottom quadrant of that slide. And in the right bottom quadrant, the red servers, those are app servers. And those are essentially stateless front-end application servers. They don't store anything locally. All of the data that they need to persist goes either into MySQL or goes into MongoDB, and that's it. So that means we can have as many or as few of them as we want. So one is fine, but if we need more, then we can have more. And because all of the communication to the front-end servers is either straight up web content, so stuff that's being delivered to users' browsers, or REST, and therefore everything uses HTTP and HTTPS everywhere, we can easily stick these front-end app servers behind an HTTP load balancer, and we're done with it, right? Very simple stuff, basically. So the app servers are really, we can have as many or as few of them as we want. They scale horizontally and so forth. So what do we do to deploy all of that in an automatic fashion? What do we use for that? Of course, Ansible, right? OpenEDX, and this is nice about OpenEDX, it includes as part of the AGPL license stack the EDX configuration GitHub repo, which is a bunch of Ansible rules and playbooks to fully automate the deployment of an OpenEDX environment. Now, in principle, OpenEDX is platform agnostic. That means you can take these playbooks and run them directly against bare metal servers running Ubuntu. You can run it in VMware or KVM, virtual machines. You can run it on AWS. That's what EDX.org uses themselves. You can deploy OpenEDX in Docker containers. There's a project, it was recently renamed. It used to be called OpenEDX Docker. It's now called Tutor, that you can use to spin up OpenEDX in Docker containers. But for the rest of this talk, I'm going to be focusing on running OpenEDX on OpenStack. So what do we need in order to run OpenEDX on OpenStack? What are sort of OpenStack's constituent parts that we can use to build our systems architecture? In other words, how do we apply this schematic to an OpenStack private or public cloud? And it turns out that, of course, OpenStack already does give us almost everything we need. Well, it does give us everything that we need here, which is we can manage virtual machines with OpenStack Nova. We get the persistent storage that we need for the database backends with OpenStack Cinder. We get networking between all those with OpenStack Neutron. We get load balancing with Octavia. And so we have already all the moving parts that we need. So how do we pull all of that together? Again, another OpenStack constituent project, we use OpenStack Heat. Now, Heat is the orchestration component in OpenStack, which means that we can define effectively an arbitrarily complex Heat template, simple YAML, that can contain any number of servers, any number of networks, routers between them, volumes. We can toss configurations out there and so forth. So Heat comes in extremely handy in firing up our OpenEDX environment. It is, admittedly, again, not the only way to do it. Another option would be, for example, to use Terraform. You can use Terraform with its OpenStack provider to spin up the scaffolding for OpenEDX in an OpenStack cloud. But Heat is a good and effective way to spin up an OpenEDX environment very quickly. Another constituent project of OpenStack that comes in very handy is Glance. Specifically, we make a very heavy use of Glance for the app servers. The principle goes like this. When we initially deploy an OpenEDX platform, we spin up one app server from a baseline Ubuntu Xenial image. We configure that master app server from the Ansible playbooks. We take a snapshot from of this server, thereby creating a master image. And then from that baseline image, we spin up as many app servers as we want. That's for the initial deployment. And conveniently, we can use a very similar process for rolling minor upgrades because of the stateless nature of the app servers, which means it works roughly like this. Again, basically, we can spin up an app server from the previous master. We can then run apt upgrade and whatever else the Ansible playbooks do for us to basically have the latest and greatest of what we want to run. So now we have a new master image. Now we deploy additional app servers from the new master image, stick those behind the load balancer, throw away the old ones, and we have a complete rolling upgrade of our front-end servers with practically zero downtime, which is nice. Now, up to this point, I've only looked really at OpenStack as one of the many platforms that we can run OpenEDX on. But that's really only one half of how OpenEDX can integrate with OpenStack, and indeed it is the less interesting half. And the other half, which is much more interesting, is the ability to provide on-demand interactive lab environments. Now, why and how is this useful? Allow me a quick detour. Consider that practically every technology, new technology that was of note and that was developed in recent years has been in nature complex, distributed, and built with scalability in mind. So just to name a few examples, think of Kubernetes, think of Ceph, think of OpenStack itself, right? And those systems are rather quite different from the ones that we saw just a few years ago, because you can think of properties like loose coupling or asynchronicity or elasticity. Those properties are not the ones that we typically worried about for the majority of the systems that we built 5 or 10 years ago. Whereas if we build them now, those properties are pretty much table stakes. So they're kind of expected. Now here's the problem, or the challenge. People comfortable with building and operating such complex systems are rather rare, and they are in very high demand. And this presents a problem for organizations who are struggling to adopt these technologies precisely because they lack, having enough people that feel comfortable with them. So we're dealing with a skills gap, not with a technology gap. And that means that as someone like me or my team, we build learning systems, and the onus is on us to provide learners, that is potentially all of you, with complex, distributed, realistic systems to use as learning environments. Something that's defined as something that you can play with and break with no repercussions. And of course, we must enable you to learn from anywhere and at any time and on your own pace. Now, suppose you are a novice to Ceph, just for the sake of discussion. Suppose you're a novice to Ceph and you want to learn Ceph. If I subject you to the joy of downloading gigabytes upon gigabytes worth of virtual images just so you can spin up a reference Ceph cluster, that's not going to make a stellar learning experience, because number one, you're likely not in possession of a laptop that comes close to the performance of a modern server as far as memory and CPU and so forth is concerned. And secondly, much less so for 10 of them, which is kind of the minimum size for a decent Ceph cluster. So making these lab environments available for you sort of the conventional way doesn't work very well, but we totally can do that when you're using cloud technology. Like giving you 10 servers, not a problem. We can do that in 2 minutes. So again, going back to OpenStack Heat, this comes in super handy, because with OpenStack Heat, we can, or a course author can define an exactly reproducible, self-contained learning environment that consists of, say, 10 servers and 3 networks connected by 2 routers, and we can toss arbitrarily involved configurations at them. And if we use that as the definition of a learner's lab environment, we can give every learner, that is to say, potentially every one of you, an exactly defined working lab infrastructure for whatever technology you want to learn and we want to teach, however complex that infrastructure needs to be. Question remains, however, how do we make all of that play nicely with an OpenEDX learning environment? And to explain that, let me introduce you to XBlocks. XBlocks are OpenEDX's plugin system that allows their authors to expand the LMS's functionality, the learning management system's functionality. And XBlocks exists for very diverse learning purposes. So for example, there's like chemistry courses on OpenEDX platforms out there that use XBlocks that allow you to do molecular modeling, like 3D molecular modeling in a chemistry course, right? Or solve mathematical equations or things like that. But if we want to provide a learning environment for distributed infrastructure and software, and we want to use that with an OpenStack private or public cloud, there is an XBlock available that spins up a course author-defined stack on demand and makes it available to learners exactly when needed, right? And here's what that looks like. So what you see there is actually such a lab environment. Oops, sorry. That is part of an OpenEDX managed course. This thing happens to be a course that covers Ceph, right? And you actually have access to a bunch of servers in here. right? Like that. So like these are real, like virtual environments. I mean, in principle, they could even be bare metal. But these are just virtual systems. And these virtual systems at this stage actually run. Oops, missing something. Actually run a working Ceph cluster. And providing or provisioning that environment, all I had to do is basically open up this page, this lab page in my course. And then magic happened to spin up a lab environment in an OpenStack cloud, any OpenStack private or public cloud that we have access to, and gave me all of this, okay? Which is really nice, and which means that you don't have to rely on the availability of potentially very expensive hardware to actually start learning the technology that you want. And like I said, this is not limited to Ceph. This could be an OpenStack course. This could be a Kubernetes course. This could be whatever. So I mentioned that this is a, hang on one second. This is interesting with the, oops, that's not what I wanted. I wanted this, and I wanted that. There we go. And so I want to proceed. Oh, by the way, just in case you're curious, right? That's a whole number of resources that were created for this specific course, right? And this could be anything. This is like 3 servers and 3 networks and 3 subnets and 1 router and a floating IP and all sorts of things. Now, an X block can have functionality that runs on the server, on the LMS, and it can have functionality that is being rendered on the client's browser. And in case you're wondering how exactly we're doing that, I'm having trouble here with my pointer. In case you're wondering how exactly that happens, which is running rather complex and long-running tasks from within the processing of an HTTP request, we do that with Celery. And that thing down there, that little Celery stalk, that is actually the Celery logo. Celery is an asynchronous task queue and processing framework. So basically, it's a facility that allows an application to say, go do X, and then continue whatever it was doing while X is asynchronously being completed in the background. This is quite frequently used in Django applications as a standard Django design pattern, where you use Celery to offload asynchronous tasks and therefore not hold up the synchronous request processing queue. And in the X block that I was talking about, what we use is we use Celery for wrapping Python Heat client, which is the Python client library for OpenStack Heat, in a Celery task, and fire that off, and then report back the task's outcome. And like I said, like the slide implies here, this can be any public cloud or it can be any private cloud. It doesn't have to be the same OpenStack that the rest of the system runs on. The rest of the system doesn't even have to run on OpenStack. You just point it at an OpenStack public or private cloud that you have API access to. And it needn't even be one. It can be multiple that you can point it to. And you can configure it to the point of where you're saying, OK, well, I'm anticipating 250 learners in this course. So I want to run 50 lab environments here and 50 lab environments there and 50 lab environments there. And we'll happily do that. You may be wondering, why am I so adamant about using OpenStack as the lab resource cloud, so the cloud type where we're running our lab resources? Is this because he's just an OpenStack zealot? Because OpenStack Heat has workalikes on other cloud platforms. So if you're familiar with AWS, AWS CloudFormation is basically Heat's workalike in AWS. If you're working with Google Cloud Deployment Manager is the OpenStack Heat workalike on that platform. So can we not use those? And at least for the time being, the answer is no, and that is not the X block's fault. Indeed, it is due to the fact that OpenStack Heat has a very critical feature that the others don't, which is the ability to suspend an entire stack, however complex that stack may be, in place, and then resume it at a much later date and return it to the exact same state as it previously was. And to be precise, that suspend operation is a bit of a misnomer because what it actually is if you're familiar with libvirt terminology, it's what libvirt calls a managed save. And a managed save operation means that for a VM that's running, its memory contents are written to a file on the hypervisor host, and then the VM shuts down. And of course, when it's later resumed, it gets started, paused, read the memory back, and then unpause. But the important and crucial point here is that while it's suspended, it doesn't consume any CPU cycles or RAM. And that's what cloud providers charge you most for. And this comes in super handy in the training lab use case, because if we're talking about self-paced training, a typical duration that a learner will spend in a lab is 30 to 45 minutes, 30 to 45 minutes that they're spending on each lesson. And they might be doing one such lesson every day or every other day. So over the course of a month, say, learners might be using their lab infrastructure for perhaps as little as 10 hours in total over that month. But if I kept that same lab running over the entire month at a cost of in excess of $1,000, that would make it entirely cost prohibitive, right? It's like you wouldn't want to afford a course like that, and it would be completely impossible to make courses like this available for free to anyone. But if we're making the lab available with precision and only when needed, meaning only when a learner actually wants to interact with it or is actively interacting with it, we can drive this price point down into double digits, which makes the entire endeavor entirely affordable. So rather than talking about infrastructure costs of $1,000 a month, we're more in the ballpark of $50 a month. Now, how exactly does that work? This is what we do. When we spin up a stack, when the X block spins up a stack, so it talks to a remote heat, spins up a stack, stack comes up successfully, we record its creation timestamp in a database. And then we have a little HTTP endpoint. As I said, X blocks can expose both server-side and client-side functionality. The X block exposes an HTTP endpoint on the LMS, HTTPS, of course, that listens to keep alive posts from the client. So the client does an AJAX post, does that every 30 seconds. And whenever we receive such a keep alive message, we update the timestamp for the corresponding stack. And if the learner now closes their browser tab, which incidentally was what I just did with my lab, if I close my browser tab, or I suspend my laptop, or I lose my network connectivity so I can no longer interact with it, the stack timestamps don't get updated. And then server-side, we have a little suspender job that runs every minute. This is configurable. Scans the database for any stacks whose most recent keep alive timestamp is more than 2 minutes. Again, configurable. And if anything has not been used, has not been interacted with in 2 minutes, or, well, not, like as I said, no keep alives. So that means browser tab closed or anything like that. If we don't get keep alive for 2 minutes, we fire off a heat stack suspend command, right? And the whole stack gets suspended. When the user returns to their lab, we just resume the stack instead of firing up a new one. And I'm going to show you in just a second how that works. But before that, I want to explain how do we actually get something that the learner can really interact with. And the way that we do that is with Apache Guacamole. Guacamole is essentially a many protocols to WebSockets gateway in a nutshell. There is a server-side daemon called guacd, written in C, and it's a very efficient daemon in translating protocols like RDP, VNC, SSH into what is called the Guacamole protocol. There's support for other protocols in the works. So for example, one development effort that's currently ongoing is one to support Spice. And another one is to directly make Guacamole an X server. So you can have Guacamole directly act as an X server, and you can have applications talk directly to it. And the protocol, the Guacamole protocol that guacd emits, is then read by a Java servlet, which is called Guacamole. Confusingly, this is sometimes named the Guacamole client because it acts as a client to guacd, although it's very much a server to the user. And then that gets translated into the WebSocket protocol, and it can then be consumed by the Guacamole JavaScript client, which runs in the browser. Okay, lots of moving parts, but it tends to work really well. So let's see. Does this work? So here we go. So I just went back to my lab. And this lab has now been suspended because I have been chatting for more than 2 minutes here. And so now when I come back, this should take about maybe a minute. And then we should drop right back into our session. I should perhaps mention that this course here uses all the interaction that the learner does is via a terminal. But if a course wants to expose GUI functionality, then that is totally possible via RDP. We chose RDP here over VNC because it just happens to be the more efficient protocol. And there is an implementation that works quite well on recent Linux distros with the EDXorg, XRDP, Xserver. So basically, again, this is an X server, but it doesn't actually talk to graphics hardware, but instead it talks to, there we go, so there's a little bit happening right now. It doesn't actually talk to graphics hardware, but it talks to, it speaks RDP on the other end, right? So now that worked rather nicely, right? And it came back nicely, and we got dropped right into where we were. But you may be thinking at this stage, well, hang on. So how exactly does that work if we are really dealing with this other protocol, which happens to be SSH, right? So you may ask, wait, so we've got Guacamole that has an SSH session open to the learner's terminal on the stack, and the stack suspends, and we've already learned the suspend is not just a sig stop, but it actually gets shut down. Then surely the SSH session is going to hit some timeout and drop, right? So how do we get the user's terminal, the learner's terminal, to look exactly like it was? What do we do to preserve that SSH connection? And the answer is we don't, because we don't have to. Instead, we use a clever little screen hack. If you stick this into a user's .profile, and they just create a new SSH connection, then by having the exec in the .profile, they will do what the screen command implies. If you're not familiar with the options here, dash lowercase x capital R means reattach to the last screen session that you were previously attached to. If none exists, create a new one, right? And so with that, you easily drop into this. And so that's how we ensure this kind of continuity. Of course, for RDP-based sessions, we don't need any such magic, right? Because for RDP, we have that built into the protocol. It always reconnects to the state of an existing desktop in the state that it was left, right? Now, another thing that comes in really handy here is a really nice way of providing feedback to the learner, and we call that progress checks. We have the ability for a course author to define a progress check at the end of every lab. And this progress check is initiated by the learner by clicking a button. And when you do, then there is a process on the LMS that shells into your lab and then executes a set of commands or a script. And right now, that's a super simple SSH implementation around Paramiko. So basically, shell in, execute a command. If it exits with 0, that's a pass. If it exits with 1 or exits with anything else, is a fail. But we're currently looking to re-implement that around robot framework. At least that's what we're considering, like get a little bit away from the homegrown stuff. And there's also a conditional facility that allows us to hide a lab from a learner if the prerequisite lab hasn't been completed successfully. And I can show you that really quickly as well. There we go, right? So here in this case, I should already have completed all the steps that were defined here in the lab instructions up top, right? And now I can go say check progress. And now there is something that actually shells into my system and checks whether I have completed the steps that were prescribed. And it then says, OK, fine, you've completed 4 out of 4 tasks that were defined, and you can now proceed. And just to show you how that then works, if I go back, for example, here to my course overview, And hang on. So for example, here I've already done, wait, no, I haven't done this lab. So if I go here, I just completed the first lab. I go to the second lab, and that becomes immediately available to me. But if I go to the next one, keep losing the pointer here. But if I go to the next one, here, there's one on OSDs. Do that. And down here, I can read the lab instructions just fine. But here it says, hang on, you still have to complete the previous one, because those are the prerequisites for running this lab. Right? This is, of course, entirely optional. This is at the course author's discretion. You can totally have labs that do not build on prior ones and are completely independent. And then also in the cost savings department, there is another nice little feature that we do have, which is the ability to, there we go, which is the ability to automatically clean up labs when they haven't been suspended for a while, when they haven't been used for a while. We call that the Reaper. Uses similar data as a suspender, although it checks the database not for when a stack last sent its keep alive, but when it was last resumed, when it was most recently resumed. And if that hasn't happened again, this is configurable, but we use a period of 2 weeks. If a lab hasn't been interacted with at all in 2 weeks, then we clear it out, because there are some resources still that a cloud service provider does charge you for, like, for example, allocated disk space. That is something where you're typically not only charged when the VM is running, but all the time. And also, there's another very precious resource in public cloud environments if you build your lab environments on IPv4, and those are public routable IPv4 addresses, right? And cloud service providers normally don't appreciate if you hold on to those for longer than you need. Now, everything that I have been talking about is something that you can try out. If you permit me a bit of a plug, on the website, the OpenEDX learning website that we run, City Cloud Academy, that's academy.citycloud.com. We do have a number of courses on there that where every month we make a contingent of seats available for free on a first-come, first-served basis. Currently, that covers our OpenStack and our Ceph course. So if you're interested in learning or refreshing your OpenStack knowledge or your Ceph knowledge, then by all means, feel free to grab one of those. We might run short of seats at this point for the January course run because of the opensource.com article that came out, but there will be more next week on the 1st of February. So if you're interested in that, then you can totally do that. And just so you know, this talk here is, as always, Creative Commons. If you want to use it, then by all means, you can. And with that, and with my image attributions, I am taking a quick look at the questions that came in, because I believe I have 3 minutes, right? Is that just about right? OK, question from Matt. How long does a resume take? I think you saw that, right? It's about 1 to 2 minutes, typically. This is somewhat dependent on the hardware of the underlying cloud platform. So for example, a resume, things like both the initial spin up and the resume can, for example, be quite significantly faster if the underlying infrastructure uses Ceph, because it does interesting things with snapshots and that sort of thing. And but yeah, round about 1 to 2 minutes. And perhaps to also add, how long does initial spin up take? Again, very much dependent on what the course author defines for the complexity of the lab, and also somewhat contingent or dependent on the underlying cloud infrastructure. But our general rule of thumb is you always want to keep this to lower than 10 minutes, and ideally to lower than 5 minutes, because otherwise your learners are really going to dislike you. So hang on. I'm just going to go back. OK, I think we have time for maybe one more question. 30 seconds. OK, well, then I will be happy to take your question outside, if you meet me outside. And I thank you very much for coming. It's always a great pleasure to be here and to talk at LCA. You people are wonderful. Enjoy the rest of the conference. Thank you very much.